You're standing still right now, reading this. Feet on the ground, not moving, wrong. You're moving at 1,000 miles per hour. Right now, as you read this sentence, that's your velocity from Earth's rotation. The planet spins, you spin with it. At the equator, 1,040 miles per hour. In New York, about 800 miles per hour. The ground beneath you is screaming through space, and you don't feel a thing. But that's not all. Earth orbits the sun. That motion, 67,000 miles per hour. You're moving at 67,000 miles per hour right now. Not metaphorically. Actually, the planet is falling around the sun in a continuous arc, and you're falling with it. The sun moves too. It's orbiting the center of the Milky Way galaxy at 514,000 miles per hour. Everything in the solar system, planets, asteroids, you dragged along for the ride. The galaxy itself, moving through space at about 1.3 million miles per hour relative to the cosmic microwave background. That's the afterglow of the Big Bang, the closest thing we have to a universal reference frame. Add it all up, you're never standing still, not even close. You're moving through space at over 1 million miles per hour in multiple directions simultaneously, and you can't feel any of it. Why not? That's the question. That's where the real physics lives. Not in the impressive numbers, though they're real, but in understanding why motion at these speeds is completely invisible to you. Why you can pour coffee in an airplane moving at 500 miles per hour and it falls straight down into your cup. Why experiments done on Earth give the same results as experiments done on a spaceship. Why there's no experiment you can do, sealed inside a room with no windows, to tell if you're moving or not. The answer demolishes the intuitive picture of motion most people carry around. It reveals something fundamental about space, time, and what moving actually means. Let's start with what motion is not. Motion is not something you possess, like having a fever or carrying a briefcase. You can't measure your motion the way you measure your temperature. There's no thermometer for velocity. Why? Because velocity requires a reference frame. You're moving at 67,000 miles per hour relative to the sun, 0 ampere hour relative to the chair you're sitting in. Both statements are completely equally true. Neither is more real than the other. This sounds like philosophical wordplay. It's not. It's operational physics. Here's how we know. Galileo figured this out in 1632. He imagined being below deck on a smoothly sailing ship. You've got flies, fish in a bowl, a bottle dripping water. Question: can you tell the ship is moving? His answer: no. The flies buzz the same way. The fish swim normally. Water drops fall straight down into the bottle. Everything behaves exactly as it would on land. No experiment reveals the ship's motion. This isn't a limitation of 17th century equipment. It's fundamental. Galileo was describing what we now call an inertial reference frame, any frame of reference moving at constant velocity. The physics is identical in all inertial frames, not similar. Identical. Newton formalized this. His first law, an object in motion stays in motion unless acted on by a force. Sounds simple. The profound part is hidden. It means uniform motion is indistinguishable from rest. They're the same thing physically. The only motion you can detect is change in motion, acceleration. This is why you don't feel Earth's rotation or orbit. Those motions are essentially constant. You, the ground, the air, the coffee in your cup, all moving together at the same velocity. No relative motion, nothing pushing you, no force, therefore no sensation. When the motion changes, you feel it instantly. The car accelerates, you're pressed into the seat. It brakes, you lurch forward. It turns, you lean sideways. Those are accelerations. You're detecting forces, the seat pushing you, the seatbelt restraining you, not motion itself, the change in motion. But here's the thing that makes this genuinely strange. Earth's orbit isn't constant. It's constantly changing direction. You're moving in a circle around the sun, and circular motion is accelerated motion. You should feel a force. Do the math. Earth's orbital radius, 150 million kilometers. Orbital period, 1 year. Centripetal acceleration from circular motion, about 0.006 meters per second squared. Compare that to gravity. 9.8 meter per square. The orbital acceleration is about 0.06% of gravity. You can't feel it. It's swamped by everything else. Your weight, the chair pushing up, thermal motions of molecules. But it's there. A scale sensitive enough could detect it. Earth's rotation is bigger. At the equator, rotational acceleration 0.034 meters square, about 0.3% of gravity, still imperceptible but measurable. People actually weigh slightly less at the equator than at the poles because of this. Bathroom scales don't notice. Precision instruments do. So the motion is real. The accelerations are real. We can't feel them because they're small compared to the forces we're used to. But the principle stands. Accelerated motion produces detectable effects. Uniform motion doesn't. Now, add the sun's motion around the galaxy. That's circular too, but enormous. Orbital radius, about 26,000 light years. Orbital period, 230 million years. The acceleration from this, about 10 circumflex, 10 meter per square, 1/10,000,000th of Earth's gravity. Completely negligible for any human-scale experiment. The galaxy's motion through space. Even worse, it's roughly straight-line motion relative to the cosmic microwave background, which means negligible acceleration. And it's so smooth that any tiny accelerations average out over the time frame of any experiment we could do. Here's what this reveals. The universe has no preferred reference frame. There's no cosmic background, no fixed stage on which everything moves, no absolute rest. When Newton wrote his laws, he assumed absolute space, a fixed framework against which all motion could be measured. He was wrong. Einstein proved it. Special relativity, 1905. The speed of light is the same in all inertial reference frames. Not just measured as the same, actually, fundamentally the same. 299,792,458 meters per second. No matter how you're moving, this has bizarre consequences. If you're moving toward a light source at half the speed of light, you don't measure the light approaching you at 1.5 times light speed. You measure it at exactly light speed. If you're moving away at 99% of light speed, you still measure light at exactly light speed. The only way this works is if space and time themselves are not absolute, they're relative. Moving clocks run slow, moving rulers contract. These aren't optical illusions, they're physical realities, confirmed by thousands of experiments. Muons produced in Earth's upper atmosphere reach the ground only because they're moving so fast that their decay time dilates. GPS satellites must correct for both special relativity, they're moving, and general relativity, they're in weaker gravity, or they'd accumulate errors of miles per day. So when you ask, am I really moving, the universe answers, relative to what? You're stationary, relative to the ground. Moving at 67,000 miles per hour, relative to the sun. Moving at different speeds relative to other stars, galaxies, distant quasars. All true simultaneously. Motion isn't a property you have. It's a relationship between you and something else. This is fundamentally different from how we think about other properties. Temperature isn't relative. You can measure it directly. Mass isn't relative, at least not in everyday experience. But velocity, pure relationship. What about the cosmic microwave background? Isn't that an absolute reference frame? Interesting question. The CMB is the oldest light in the universe, the afterglow from 380,000 years after the Big Bang. It's nearly uniform in all directions, but Earth's motion creates a Doppler shift. Moving toward one direction, the CMB looks slightly hotter. Moving away, slightly cooler. From this we can calculate Earth's peculiar velocity, about 370 kilometers per square, toward the constellation Leo. Does this define absolute motion? No, it defines motion relative to the CMB's rest frame. That's a special frame, the one where the CMB looks most uniform. But it's not privileged by physics. The laws of physics don't care about it. You could do all your experiments in a lab moving at 99% of light speed relative to the CMB, and you'd get identical results. The CMB gives us a convenient reference, but not a fundamental one. Motion remains relative. Here's why this matters. Your intuition evolved for survival on an African savanna, running prey, avoiding predators, throwing rocks. In that environment, the ground is the natural reference frame. Everything else moves relative to it. This works beautifully for speeds up to maybe 30 miles per hour and durations up to a lifetime. Your intuition did not evolve for speeds of 67,000 miles per hour. It did not evolve for comparing reference frames moving at different velocities. It certainly didn't evolve for speeds approaching light speed, where time dilation and length contraction become significant. So your intuition lies. It tells you motion is absolute, that there's a fact about whether you're really moving. that if you could just step outside the universe and look, you'd see what's actually moving and what's actually at rest. You can't step outside the universe. There is no outside, and there is no fact about who's really moving. Think about what this does to the concept of rest. Rest doesn't mean not moving. It means not moving relative to a chosen reference frame. Usually that frame is Earth's surface, but you could just as validly choose a frame moving at constant velocity relative to Earth. In that frame you're moving, Earth is moving, and someone floating in space nearby is at rest. The physics works identically. When physicists say all motion is relative, they don't mean it's subjective or arbitrary. They mean there's no physical experiment that can detect absolute motion. You can only detect motion relative to something else. And all inertial reference frames are physically equivalent. This has practical consequences. When engineers design spacecraft, they don't worry about the spacecraft's absolute velocity. They care about velocity relative to Earth, relative to the Sun, relative to the destination. Those are what determine fuel requirements, travel time, trajectories. When particle physicists accelerate protons to 99.999% of light speed at the Large Hadron Collider, they're not worried about Earth's motion through space. They're accelerating the protons relative to the lab. That's what matters for the collisions. The universe doesn't care about absolute motion because there is no such thing. Now one more layer. I said accelerated motion is different. You can detect it. That's true for linear acceleration, speeding up or slowing down. But what about rotational acceleration? Newton thought rotation was absolute. A bucket of water spinning on a rope. The water climbs the sides. Stop the bucket. Keep the water spinning. Same effect. He argued the water knows it's rotating, even if nothing else in the universe is moving. This bothered Ernst Mach in the 1880s. He proposed that inertia resistance to acceleration comes from all the other matter in the universe. You can't tell if you're spinning in an empty universe. Rotation is also relative, defined by motion relative to the distant stars. Einstein took this seriously when developing general relativity. He called it Mach's principle. The math gets complicated, and the issue isn't fully resolved. But experiments with spinning gyroscopes in space suggest Mach was onto something. Frame dragging, the way rotating masses twist spacetime, implies that rotation is at least partially relational. So even rotation, which feels absolute when you're spinning in a chair and getting dizzy, might be relative to the rest of the universe's matter. What's left, what's not relative? The speed of light, absolute. The laws of physics, absolute. They're the same in all inertial frames. The space-time interval between events, absolute. Though space and time separately are relative. Causality, absolute. If event A causes event B in one frame, it causes B in all frames. But velocity, completely relative. So when you stand still, you're not still. You're moving at hundreds of thousands of miles per hour in multiple directions. When you sit in a train and watch another train pass, you can't tell which train is moving. Both perspectives are valid. When astronauts orbit Earth at 17,500 miles per hour, they're also at rest in their own reference frame, and Earth is moving past them at 17,500 miles per hour. All of this is true. None of it is metaphor. The universe has no stage. There's no fixed background. Motion is always motion of something relative to something else. And that's not a limitation of our knowledge. It's how motion fundamentally works. You're never standing still, but neither is anything else.